Alright, so let's try an example using the Laplace transformation to solve an initial value problem. And here are some of the most often used Laplace transform results. That Laplace transform t to the n e to the at is this one. I guess the more used one will be when n is equal to 0. Do you know what's 0 factorial? What's 0 factorial?
1.
1. 0 factorial is 1. You probably learned that when you're doing Laplace, Taylor series. Okay. 0 factorial is 1, and therefore when there's no t, you will just have 1 over s minus a, because if n is 0, that's what you're going to get. Okay. So this result can be also read as this result can also be used for just e to the at, where n is equal to 0, which just says it's 1 over s minus a. And also another case will be when it's just t to the n, when a is 0. If a is 0, you get n factorial over s to the n plus 1. Okay? So this one result actually says two things at once. And there's also these rules for e to the at sine bt, and of course you can also use this for the case when a is 0 or b is 0. They would say individual results. Same thing over here. Okay, let's try an example here. So let's try the following. Y double prime minus 3y prime plus 2y equals to 6 sine 2t with y of 0 equals to 1, y prime of 0 equals to 0. Let's try this. Okay, first apply Laplace transform. This one transforms to this thing here. So 2 derivatives gives you s squared, and the initial conditions pop up. The initial values are used. This one is negative 3 sys minus y of 0. That's another formula that if you apply Laplace transform to y prime, you get this. In fact, this result here can be obtained just by using this. I explained somewhere before. Okay, and then plus 2y. So it's just y, a regular function of y, y of t. The regular function yt gets transformed to y of s. Now let's think about sine of 2t. You can use this thing with a equal to 0. So it will be b over s squared plus b squared, where b is this thing. So what's b for our case? What's b for our case?
2.
2, right? So it's 2 over s squared plus 4. Which then times 6 gives you 12 over s squared plus 4. Now use the initial conditions. This is 1, that's 0, that's 1. So you have s squared ys minus s, that's 0, minus 3s ys, that's 1. Negative 3 times negative 1 is plus 3. So it's 2ys equals to 12 over s squared plus 4. Collect the y's's together, so it's s squared minus 3s plus 2 ys. And then s and 3 goes to the other side. So that becomes s minus 3. And then plus 12 over s squared plus 4. Now you divide this to the other side, but before you divide, it's good to factor s minus 2 s minus 1. So this is what we're going to divide to the other side. If I divide, I get y of s equal to s minus 3 over s minus 2, s minus 1, plus 12 over s squared plus 4, s minus 2, s minus 1. Okay. Now we're going to be a little lazy here. We're trying to do partial fraction expansion, meaning that you're trying to make these as a bunch of fractions with these being individual ones. Right? Usually you're taught that you have to combine these two together, and then if you have one big fraction, then you split them according to each one of these. But we don't want to do that. We can just split it right now. But just imagine what's going to happen. If you combine them, what will be the denominator? The common denominator would be this one, by multiplying s squared plus 4 top and bottom, right? So assuming that we did that, if we have this as the common denominator, then you can split this on the right side in the following way, right? It's for s squared plus 4, you would need s squared plus 4 here. And since this cannot be factored, you have to leave it like this. And because it's it's a quadratic polynomial, on the top you have to put one less order. Since this is a second order polynomial, you have to put a first order polynomial. So we're going to put as plus b. And then for s minus 2, I'm going to use c, s minus 2. And for s minus 1, I'm going to use d over s minus 1. And what we need to figure out is what is a, b, c, and d. Once we figure out a, b, c, and d, then we can figure out exactly what y of s is. Y of t is, the original one. The beauty of Laplace transform is that you started with a differential equation, and suddenly it just becomes an algebraic equation, which you can solve. But the problem is, this is not what you're looking for. You're looking for y of t, not capital Y of s. So to go back from y of s to y of t, you somehow have to use these. You have to be able to go back from a given transformed one to the previous function. And to do that, you have to make it into partial fraction expansion, because if you do that, then these individual ones, I know where they came from. Okay? Any questions up to here? If there are no questions, let's continue on with this calculation. Okay, what I'm going to do is I'm going to take this equation and multiply both sides by this. So I'm going to take s squared plus 4 times s minus 2, s minus 1. I'm going to multiply this to the first one, which is s minus 3 over s minus 2, s minus 1, plus s squared plus 4 times s minus 2, s minus 1 has to be multiplied to the second one, 12 over s squared plus 4, s minus 2, s minus 1. And on the right side, I'm going to put the right side down here. It will be s squared plus 4, s minus 2, s minus 1 times as plus b over s squared plus 4 plus s squared plus 4, s minus 2, s minus 1 times c over s minus 2 plus s squared plus 4, s minus 2, s minus 1 d over s minus 1. So I just multiply this thing to all the terms that you see in the equation. Now I'm not going to be this nice next time. I just want to show you what I'm doing, but from now on I'm just going to skip this step. You should just know that if I multiply this, for the first one these will cancel, leaving you with this times that. They're all going to cancel, leaving you with 12 by itself. This will cancel, this will cancel, this will cancel. Okay. So you should know which ones cancel and which ones survive after multiplying this. That should be kind of obvious. All right, now let's see what we get after canceling. So first we have s squared plus 4 times s minus 3 plus 12 equal to s minus 2, s minus 1, as plus b plus s squared plus 4 s minus 1 times c, s squared plus 4 s minus 2 times d. And what we have here is an equation among functions of s. A, B, C, D are some unknown coefficients to be determined, and both sides should equal as functions of s. Meaning that whatever value s takes, the two sides should produce exactly the same answer. Okay? So that means we're free to plug in anything for s. And I choose s to be 1 because I know that if s is 1, this becomes 0, getting rid of this entire thing. If s is 1, that also becomes 0. This one survives, right? So we get an equation in D which we can easily solve. So let's see. If s is 1, 1 plus 4 is 5 times negative 2. That's negative 10 plus 12, which is just 2. This is 0, that's 0. 5 times negative 1, so that's negative 5d. Giving you that d is negative 2 over 5. And then what else should I plug in?
3.
2. 2. Yeah. Because 2 would get rid of this one, also that one, leaving you with only c. Right? Okay, 2 squared is 4. 4 plus 4 is 8. So it's negative 8 plus 12. That's gone. This is 4 times negative 8c. And then the last one is also 0. So that's all you get if you plug in s equals to 2 both sides. And that gives you c equals to negative 1/2.
Would be positive.
Positive 1.
Oh, is it?
Yeah.
No. If I plug in 2 squared, that's
No,
4
on the right side.
On the right side, 2
2
squared
minus
is
1.
4. 4 plus 4 is 8. 2 minus 1 is positive 1. Oh, you're right. Okay, so it's positive 1. Thank you. All right, and then s equal to 0. I chose s equal to 0 because if I do that, then a is gone, right? So I can figure out what b is. All right, so if s is 0, you get 4 times negative 3, which is negative 12 plus 12. That's 0. Okay, 0 is equal to, this is negative 2 times negative 1, positive 2b. Okay, and then negative 4c. The last one is negative 8d. Okay. So if I move this to the other side and divide by 2, if I divide by 2 and move everything to the other side, I get b equals to 2c plus 4d. And 2c is 1. 4d is negative 8 over 5. It's negative 3 over 5. All All right, then we run out of nice numbers to plug in. See, I chose 0 and 1 and 2 because those are the ones that delete some variables, and you can just solve for the ones that survive. But then I need to find what A is, and there's not a good number to delete everything else. I mean, you have there are some possible choices that's not that attractive. These ones are like 2i. If you plug in 2i squared is negative 4, right? So these will cancel away, whereas this will survive, and you can calculate that. So that's a possible number to plug in. If you're really desperate, you might try that. Okay. There are some cases you really need to do that. Okay. But here we have another nice way of seeing this problem. That's to think about the following fact. If you have two polynomials that agree as functions, then if you expand them and organize in terms of powers, their coefficients must match. Okay? We all know that, right? For two cubic functions to be exactly same for all values of s, their coefficients must be the same. So we can expand the entire thing, we can expand this entire thing, and then compare the coefficients, and then conclude something. However, again, we want to be a little more lazy. We don't want to do the full expansion because that's going to take a long time. So we're only going to pretend that we did it, but we're only going to look at the highest order. Okay? Because if you multiply s squared times s, that's s cubed. So we're just going to look at s cubed. S cubed seems to be the highest order that the left side produces. Also the same here, right? S times as. So that's as cubed. S squared times s times c, so that's cs cubed. Okay, and then d times s squared times s, so that's ds cubed. There is no other s cubed that can be produced when you expand this, right? Nor this would have s to the fourth or anything. S cubed seems to be the highest order, and I see that on the left side it's s cubed, whereas on the right side I have as cubed, cs cubed, ds cubed. So if I were to organize this by powers, I would have to collect these three terms and put it as a plus c plus d s cubed. So this will be the coefficient of the s cubed term, and 1 will be the coefficient of the s cubed term on the left side. For these two to be equal as functions, these coefficients must match, right? So we have the conclusion that for this to work, we need 1 equals to a plus c plus d. Which means that, let's see, what's A? A is 1 minus c minus d. 1 minus 1/2 is 1/2. Minus negative 2/5 is plus 2/5. So over 10, this is 5 plus 4 over 10. So 5 plus 4. So it's 9 over 10. So that's your A. A is 9 over 10. Okay? All right, good. So what did we just figure out? We just figured out, well, I raised the original form. Hopefully you remember what it was. We figured out that ys was as plus b, so it's 9 over 10 s plus b is negative 3 over 5 over s squared plus 4. Actually, yeah, so the c over s minus 2, c is 1/2, so it's 1/2 over s minus 2 plus negative 2/5 s minus 1. That's what we figured out. And then we just have to reverse engineer these things that we have here to figure out what was the original y of t. Okay? So let's figure this out. So you have let's see, this is 9 over 10 times s over s squared plus 4. Negative 3 over 5 times s squared plus 4, 1 over s squared plus 4, plus 1/2, 1 over s minus 2, 2/5, 1 over s minus 1. Now for these, I know what they are. S minus 2, what's that? According to this. That's when n is 0, right? 1 over s minus 8. So where is this from? This is a Laplace transform of e to the... Look, if n is 0, it's 1 over s minus 8, right? What's a here for that to match with this? 2. So it's the Laplace transform of e to the 2t. What about this one? That's the Laplace transform of
E to the t.
e to the t. Yes. And then this is the Laplace transform of, oh, look at this one. If a is 0, you have s over s squared plus b squared, right? If a is 0. So where's that from?
Cosine of 2t.
So this is a Laplace transform of cosine of 2t. It really, the only challenge that you will face is when you try to do this one. The problem with this is if you try to match with this, with that, with a equal to 0, what goes wrong? If you try to match with this, with that.
It should be 2 over s squared.
It should be
plus 4.
2 over s squared plus 4, because if this is 2, then this has to be 2. But we have 1. What do? You have to borrow this from somewhere. How?
Multiply by half.
You put this as 2, and you rewrite this as 1 over 5 is same as 2 over 10. Then this is Laplace transform of sine of 2t. And then we now arrive at the final answer. What's the final answer? We have y of t equals to 9 over 10 cosine 2t minus 3 over 10 sine 2t plus 1/2 of e to the 2t minus 2/5 of e to the t. So that's the answer. Yeah, it's y of t now. We're doing the inverse. So we know that if I had this and took the Laplace transform of it, we will get these terms, which is same as y of s. So therefore, this is the answer.
Well, why'd you change the numerator? Oh, it's like...
Any other questions? Oh, good. Yeah, you have a question?
Yeah. Why is it negative 3 over 10?
Oh, okay. So it's 3 over 5,
Yeah.
right?
I see.
I want to write down negative 3 over 5 as negative 3 over 10 times 2. Now let's first make sure that this is true. If you reduce 2 and 10, it's 1 and 5, right?
Mhm.
So it's same as this, right? So you agree that this is indeed same as that.
Mhm.
Now, why would I want it to be 2 instead of 1? Well, the reason is, if you look at this formula, for a equals to 0, if a is 0, then e to the 0th power is 1, so that goes away. A is 0, so I have this formula, where b and b should be the same thing for this. See, I have cosine 2t, so probably we're looking for sine 2t, right? But for sine 2t, to be that one, we need this to be sine of 2t's Laplace transform is 2 over s squared plus 4. It shouldn't be 1, it has to be 2.
Okay.
And that's why we wanted this 2.